Andy, thank you very much. Thank you for all your help, and you have my appreciation for that, and also my appreciation to INCOSE for establishing this series and allowing me to participate. And finally, all of you have my appreciation as well for taking your time today to hear about this. I'm going to talk about feature-based product line engineering, and I think of this as the, let me say at least the current culmination of the decades of experience that we all as a community have been assembling in this engineering technique. If you're new to product line engineering, then I hope you'll be interested in this way of building systems. If you're an old hand at product line engineering, I hope you'll find the recent developments that I'm going to concentrate on here to be interesting and new for you. So what do I mean by product line engineering? This term has gained traction and footing in the various engineering communities, and that's good, but like many fields that have not yet swept the world, we don't have a single definition on which we all agree, and that's okay, that's healthy. But I mean a very specific thing by product line engineering, and so I want to say what that is, and so we can go forward with that in mind, as opposed to any of the other concepts or approaches that are out there. So first of all, a product line, I think this is largely agreed on. It's a family of similar products or systems with variations in features and functions, and that simple declaration holds the two key concepts that we're going to be working with all throughout our engagement with this engineering paradigm: similarity and variation. So the systems are like each other. It's going to pay us to consider them as a single thing and not a collection of separate things because they are similar. However, they're different. They're obviously not the same system. They differ from each other. They have variations, typically in features and functions. All right. What do we mean by product line engineering then, which I'll probably from here on out just call PLE? It's the engineering of a product line, obviously, and our approach is very specific, and it has three facets to it. First is the shared set of engineering assets. What is the physical manifestation on the engineering of these products? So these are the engineering artifacts that you use to engineer, develop, deploy, run, operate, retire the products in the product line. There is no fixed set of these. It's an open-ended set. It's a wonderfully open-ended set. That's the fun part. But in our experience, it typically includes things like requirements and test cases and user documentations. If the system or the product has software in it, it can include software code, software development plans, and so forth. So it is the artifacts that you use to develop these similar but different systems. The second aspect of PLE, which we employ, is a managed set of features. We are a feature-based approach. A feature is a distinguishing characteristic of a product. It's what sets it apart from other products. Product A might have this feature, product B might not. Or product A might have this flavor of that feature, and product B might have a different flavor of that feature. A feature is an abstraction, and most of the talk today we're going to spend discussing features. And finally, an automated means of production. So the modern instantiation of product line engineering is automation-centered. There is a tool. We make one. Our company makes one. The tool is called Gears. It's a class of tools called a configurator, and it maps the shared assets and the features to each other and produces product-specific instantiations. So this takes advantage of the commonality, and that's where the savings and the cost avoidance and so forth that product line engineering is known for comes from. We're taking advantage of that commonality every single day, and we're not duplicating work, and we're not duplicating artifacts. But we are not afraid of variation in the least. We efficiently manage and respect the variation, so we don't, for instance, require you to use a common platform or anything like that. No, we like variation, so that's okay. So that's our approach. And this is it in a slide. So here down at the bottom left are the shared assets. And we've used the system engineering V model to lay this out. This is notional, of course. You should macro in place your own V model as you think about this. So there might be requirements and codes and bills of materials and tests and acceptances and calibrations and documentation, whatever you'd like to put in there. that's fine. And the shared assets are essentially supersets. So, for instance, over here in System Requirements, second green box on the left, it's a superset. Any system requirement that applies to one or more of the products in the product line is going to be in here somewhere. And you'll note that the assets here in this V column, there are little gear symbols in there, and those stand for variation points. And a variation point, it's a very simple concept. It's simply a piece of content in an asset whose presence in the product, whose participation in the product depends on what features have been chosen. So a requirement that does not apply to every product will be a variation point. It applies to some products. And the variation point will stay as a kind of an annotation to that content under what feature choices that requirement does apply. And the same the same concept applies to all of the shared assets. A variation point could be a test case. A variation point could be a paragraph or a section or a page or a figure in a user documentation. A variation point could be a chunk of source code, maybe a block or a file or a folder of source code. And the participation of all of those different kinds of content is predicated on the feature choices that are in play as we're building the product. And so the gold lines from these variation points come up to this feature catalog, which is a construct that stores all of the features available across the product line. Those gold lines indicate that the variation points are written in terms of those features. So if this feature was chosen, for instance, for product A, then all of this shared asset content will be configured to include all of the content that's annotated for being there when that feature should be chosen. And that's how that works. Extracts from the feature catalog describe individual products. So these are all the choices that are available in the catalog. A bill of features is the construct we use to describe the features for an individual specific product. This is simply a set of choices made against the feature catalog. This is sort of the shopping, this is what's available on the shelves, and this is what you put in your shopping cart for your product. And the automation is what makes it all work. So the configurator down here configures the shared assets by exercising those variation points and including content or omitting content based on the feature choices in a bill of features. And the economics of this spring from the fact that there's no duplication anywhere. So all of the content is over here at most once, and there's no duplication to be had anywhere. And as you can see, this is quite a move away from older system development paradigms that we've had with us for decades, if not centuries, where by and large each product was its own going concern. Each product may have had its own team, may have had its own project, may have had its own developers, its own effort, and so forth. They didn't start from scratch. They may have borrowed content from each other, but once the borrowing was done, the commonality was no longer exploited. We tended to go off and just treat this as our own borrowed property now, and thanks to where we got it from, but we won't be needing you anymore. Some organizations try to CM their way out of this mess, and then everybody spends their time branching and merging and merging and branching, and they sort of forgot why they were hired in the first place. And so we don't do any of that. We're going to suppress all of that duplication in the figure that I showed you before. Well, there are roles and responsibilities associated with this picture. So we have a new role under this paradigm of feature-based PLE. It's a feature owner or a feature architect, some organizations call them. These are people who are responsible for what a feature means. So if you put a feature on an automobile, for instance, like cruise control, well, what are the capabilities of that feature? What is its functionality? What flavors does it come in, and so forth? You just can't leave that to anyone. We'll need to leave that to an expert in that subject matter area. And so feature owner turns out to be an important part. My asset engineers are the people who are responsible for the care and feeding of my shared assets. And these can be, as I said, software calibration signals, wiring harnesses for systems that need those, bills of materials for systems that need those, and so forth. And these people, by and large, do what they did before the move to this paradigm. So a requirements engineer perhaps used to work on requirements for an individual product. Well, he or she is still going to do requirements engineering, except now their purview is the entire product line. And now they work in the language of variation points. Now they annotate their content by saying what features cause it to be there. But 90% of their job is still, you know, plain old requirements engineering. Same for the software engineers and the test engineers and the calibration engineers and the documentation writers and so forth. Their jobs are largely what they were before, but now just a little bit different. A portfolio team in large product line organizations, they create the bill of features for each of the product families and flavors based on the features available in the feature catalog. So this can be sort of the control center for an organization to manage its portfolio, because it's very easy to see what offerings are possible based on the feature catalog. And so that's a new role as well. And finally, suppliers and testers and manufacturing and sales and more, they use the generated assets configured by the bill of features for a system or a product family, and that's not so different than the way it is today. Many organizations that we know do not, in fact, divulge to their customers that this is how they're building the products for them. They just say, here, we built this lovingly for you, and no need to look behind the curtain. Well, all this is predicated on this question: what's a feature? And I sort of did a drive-by on that in the early slides here. I said it's a distinguishing characteristic that sets products apart from each other. Well, that description might bear a little bit closer look. So this notion of a distinguishing characteristic, this comes from the original FODA paper, Feature-Oriented Domain Analysis, written by Keo Kang and Sholem Cohen and some other colleagues. It was an SEI report, and it is long in tooth now. It was written in 1990, so if I'm doing the arithmetic right, oh my gosh, it's almost 3 decades old. And yet that definition has served us very well. It's a distinguishing characteristic. Kang and Cohen and others were looking for a way to describe domains. Domain analysis was sort of in vogue back in the 90s, and they said we need a way to describe the products in a generic sort of domain-independent way, and so they hit upon features, and it's helped us a lot. Well, what constitutes a distinguishing characteristic? Products, at the end of the day, are differentiated by the differences in many, many places. So you can look at the digital engineering representations of 2 different products and do a conceptual diff on all of those and see what diff tells you. And those are distinguishing characteristics. I mean, they are. So requirements, objects could be different from each other, from product to product, model elements from design specs, test cases, lines of software, individual lines of software could be what differs from a product, mechanical parts in a bill of materials, a single part maybe, a paragraph or a line in a user's manual. I mean, it goes on and on and on. And so, undisputably, those are distinguishing characteristics. However, we want and are seeing feature-based product line engineering to be in use in the highest levels of organizations. And vice presidents in charge of strategic engineering decisions do not care that product A had this line in the user manual and product B had that line in the user manual. So I'm going to need something better than that to be a distinguishing characteristic. We work with some automakers, and so they probably make the largest product lines on the planet. And so the numbers I'm going to start offering you from here forth come from experience in that kind of world where I can make up to 10 million products a year. General Motors, for example, each year in their product line, they built 9.5 million cars last year in 30,000 electrically unique configurations. So that's sort of the size of their product line, if you like. 9.5 million instances, and in the electronics, 30,000 members, 30,000 configurations. So in a product line of that size, there may easily be millions and millions of those tiny little differences, this line of code, that requirement, this paragraph in a user manual. And so that's just untenable. We cannot deal with that on its own. We need larger level abstractions to help us deal with this. So the bottom line here is the bottom line on this slide. There cannot be a one-to-one correspondence between a feature and a variation in an engineering artifact. If that's all it is, then features really haven't helped us. All right. That's a duplicate slide, sorry. So some recent work in this area has laid out what we've come to call a feature ontology for feature-based PLE. And what we're going to try to do is establish, we're going to put some more substance and some more depth and some more texture into what it means to be a feature, and do this with an eye towards allowing people in different roles in a PLE organization to make use of these concepts to do their daily jobs. So what's an ontology? This is a word I love using because I don't get to very often, and so I'm going to try to use it correctly. An ontology is an explicit formal specification of the terms in a domain and relationships among them. And you can see the reference for that definition. And the goal of an ontology, besides, getting to say ontology because it's a really cool word to talk about impressing your friends, it really does have practical goals, one of which is to share common understanding of the structure of information among people or software agents. Yeah, that's exactly what we want to do. So we're going to try to really dig into the term feature and produce an ontology for it. So we're going to base our ontology on abstraction levels, where each level comprises the data structure that I work with that holds the information, that carries the information at that particular level, and it's going to be features. And then there's a notion of a feature profile, which is a set of choices that you actually make against the features that are available at that level. And then finally, the abstraction at a level, we're going to describe the abstraction itself that it presents to the next higher level. And so we're starting with a complexity range of maybe 1 million variations in an automotive-sized product line. And what we really want to get down to is a very, very small number of choices that somebody who's responsible for an overall vehicle, let's say, or an overall portfolio can make and not have their head explode. And so these levels together are going to serve the diverse feature management roles and responsibilities across an enterprise, and I've outlined some of them on the last bullet of that slide. No level is going to serve all of those roles, but the goal is that the levels together will have coverage across the roles. Well, so let's start. Distinguishing characteristics 101. We call this level 0, and it is asset variation points. It's exactly that set of things that I said we couldn't take forward, and yet we can't throw them away either. Requirements engineers need to know that the requirements for product A differ on this line than the requirements in product B. Documentation writers need to know that the user manual for product A has this paragraph, but the user manual for product B has that other paragraph. So this is important, and our asset engineers need to know this. And so at this level, we embrace it, but we say, thank you, we're going to start from here, but we're going to start climbing from here. But here the purposes and roles include the asset engineers that I just described, the data structure for the feature model at this level. Each variation point is either optional, that is the content is either optional, you can have it or omit it out of a product, or it comes in multiple, let me say flavors, but we use the word variants here. But think about a flavor of a paragraph or a flavor of a line of source code. It might come in 3 flavors, and the variation point for a particular product would pick one of those flavors. And that's how we describe the asset variations. The feature profiles are manifested in what I end up with. Either the content is in or it's out, or flavor 1 or flavor 9 or flavor 6 was chosen. And the abstraction provided to the next level, none. None. And that's why we need a next level. We need to do better than this. And so when we work with organizations to come up with what I will call the next level of features, we ask them the question, why? So I might have 2 requirements engineers in a room, and I'll say, what's different between product A and product B? And they'll point me to requirement 64, and it's different over here than it was over there. And we say, well, why is that? And when they just they may give us a question, and then we act like the 4-year-old. We'll say, well, why is that? And they'll explain another difference, and we'll say, well, why is that? Why does that matter? And eventually we'll get to a place where they're describing the difference that led to those deltas in the documents. They're describing the difference in an abstract way, and at that point we found a feature. And so this why is kind of a heuristic that we've discovered to help people articulate features at this level, which is level 1 of our ontology. We call this primitive standalone features. So the purpose here and the roles, we have feature engineers. Now I've got people who are responsible for starting to build and maintain a feature catalog for my product line, create feature abstractions that can be used to drive the root cause variation at our previous level. And this is typically responsible for driving the variations in multiple assets. So I would really like a feature to drive a difference in requirements and code and tests and documentation, so that with one choice of the value of that feature, I can drive the variation in multiple kinds of assets. That's a valuable abstraction. And in the kinds of features that we work with and we help our feature engineers discover, that's the effect that it has. And so the data structure here, each feature has a name. In our world, it has a type. So a Boolean feature is one that you can either choose to have or not. An enumeration feature is one that comes in flavors, and you can pick one flavor. A set feature is a feature that comes in flavors, and you can have any of the flavors, multiple flavors if you like, on an instance, and it goes on. So our features have names and types. The feature profile then is simply the choice you make against this primitive feature. And the abstraction provided to the next level is the feature names, types, and profile instantiations are directly provided. But now the next level, we know how these features are going to drive asset variation, but the next level is insulated from that. The next level and the people working at that level no longer need to be concerned with the assets. They can start thinking about the features in terms of capabilities. Here are two simple examples of a primitive feature. There you go, name and a type. A feature called lockout deterrent, it's Boolean. A feature called lockout status indication, it's got 3 flavors. You know, welcome to your choice. Pick any one of those 3. And so as I said before, it's these features that drive the variations over the variation points. And just by doing that, typically we see that I'm no longer dealing with a million kinds of variations. Now I'm down to sort of 2 to the 10,000. That's my space. That's my decision space. Boy, that's a lot better than 2 to the millionth. That's pretty big. Just for your frame of reference, I think 2 to the 78, I think, is the number of atoms in the visible universe. So 2 to the million is a really big number. 2 to the 10,000 is a really big number, but it's better. And so now my engineering leadership and my asset engineers are dealing at this level. Well, so I can have maybe 10,000 of those primitive features. And you can imagine a great big grab bag of those features, but I really need a way to structure them. I need a way to consider groups of related primitive features in a way together. And this is a very architectural kind of notion. I want to apply an aggregation of those primitive features into, well, aggregations of related features. And you apply architectural criteria. So coherence, cohesion. I mean, these things have to do with each other. You apply separation of concerns criteria. This feature doesn't really have anything to do with that one. I'm going to keep them apart, but oh, these two features are kind of talking about the same thing. I'll clump them together. So at this level, we produce what we call a component feature model, and it is nothing more than the aggregation, many aggregations, of the primitive features. And so the result here then is this set of aggregations. I basically clumped my primitive features into modular collections. And the data structure here is just the aggregation. The feature profiles, it's the set of choices you make against an aggregation. And now that's what we can supply as the abstraction to the next higher level. The profile is a thing I can describe independently, and you're certainly welcome to describe a profile exactly by the choices that you've made, but you can also describe it abstractly. This is a very low-end offering in this area. I've picked the lowest, cheapest choices possible. This is a very high-end offering. I picked all the possible options and variants, and it's very luxurious profile. You can describe the profiles that way and actually move away from the primitive features if you like. That choice is available to you. And so here's an example. It's just an aggregation of primitive features. This is a model for a subsystem called front climate control, and it's built out of related primitive features, and that's it. And then a profile would just look like that. It's a set of actual choices. This profile is called auto dual temp heat cool, and you could describe auto dual temp heat cool without really referring to these individual features if you wanted to. You could say this is an automatic system that provides heating and cooling in two different zones in your vehicle. There, and nobody has to go look at this model. That wording I just provided might be sufficient. And now I have an abstraction. Well, okay, so now I'm down to maybe 2 to 1,000. That's my space. We're getting there. And in a very large organization where I've got thousands of engineers working, and that's the automotive world, that's getting to be tractable. But again, I'm not to the level where executives can really deal with this, the people who make strategic decisions about the portfolio. So, but we're getting there. I can put those component feature models together in a hierarchy, and we call this level a subsystem feature model. So what we're going to do is we're going to take component feature models that are related to each other, and we're going to just simply aggregate them as well. And really, this is the game we're going to play for the rest of the ontology. We're going to just do aggregation, and we'll stop when the complexity gets where we need it to be. And again, the same criteria apply. Typically, what we see in practice is that people will apply an aggregation of component feature models in a way that reflects their system architecture for their products. And so that model that I showed you on the last slide is about front climate control for a car. And you can imagine there's a rear climate control for a car. You can imagine there's blowers and fans and heaters. And all of these belong to a system called climate control for the car. And that's where we're headed. So this subsystem feature model then is an aggregation of the component feature models, and it typically reflects the system architecture of the product that you're dealing with in the case of large and complex products that have many subsystems, such as climate control. You can imagine another one for engines and another one for steering and another one for cruise control and all of these things. So again, it's an aggregation, and again, the profiles are simply choices made against the aggregation of those models. But they're not choices of individual features anymore. Those have been left behind. They are choices of the profiles that the component models offered up. And so when I aggregate my component models together, they each offered profiles. And when I aggregate those into a subsystem feature model, the definition of a subsystem is a choice of profiles from the component levels. And that's my profile at this level, and that's what I'll offer up. And so here's an example of that. We've gone to a different representation. This could be a tree as well. We find it convenient to make it more of a list. And so here is a list of profiles for a subsystem feature model. There are 7, and they're arrayed across the left there from basic to premium plus. And this is an aggregation of 3 component models called power door locks, rear closure unlock, and fuel filler door unlock. And you can see that the choice of what defines premium plus, for example, is a profile choice for each of the component models. So we're abstracting higher and higher. The people that work at this level, this is what they need. They need to know That Premium Plus has the Premium with Digital Keypad 5 offering of power door locks, and the interior button and key fob offering of rear enclosure unlock, and so forth. And so we keep climbing up. And finally, this is the last level of our model. We have a system feature model. It is yet one more aggregation. And we do this with hierarchy. We do this by combining component models and subsystem models together, and I make that an aggregation of a pure system. And I won't go through this because I think you see the theme. Now, I'm going to take my lower level constructs, I'm going to choose profiles from each one of those, and I'm going to use those choices to define a profile of my own that I'll then offer up to the outside world. So here's another example. It looks like it did before. I've got 4 products on my left, and the 2 columns, the 2 yellow columns there, those are actually component feature models, and I've made choices against them. And then the 2 columns on the right, and there are actually many more columns on the right for this example, but I couldn't begin to put that on a slide, and so I let it tail off on the right. Those are subsystem feature models that we've drawn from, but the concept is the same. I'll pick profiles from the lower level to create my profiles at this level, and now anyone consuming these products can just think in terms of product 1, product 2, product 3, and product 4. And boy, do you remember when we were worried about lines and requirements being different from each other? We have left that way behind. And now I'm dealing at a level, an ontological and conceptual level, where executives can work with our feature catalog in a way that's meaningful to them. So here's an example of a hierarchy of a production line, and it just shows my product line at the top is called vehicle, and the tool-based name for hierarchy is imported production lines, and so those are children, and that's how you build this thing. So there's one last concept that I want to bring to bear here, because now we're sort of down in the 2 to the 50th space of complexity, and that's pretty good. But I'd still like to come down more, and it turns out that organizations that build cars, for example, that's still not a manufacturable number of combinations. It's still too big. My assembly lines would have to be too general, have too many parts, and too complex, and the factories would be enormous. And so we have to get it down even more. And we've called this level, I'm not happy with the number. It's just an overlay. It doesn't have a number. We could have done this at any level. In our implementation of product line engineering, in our tool set where we provide these constructs, we've chosen to add this concept at this level, but you could do it at any level. And here's the concept. The concept is that if you're making multiple choices across the choices that are available to you from lower level components, you'd like to be able to restrict the combinations of choices that you make. And again, those of you who are familiar with the auto industry will recognize this immediately. These are basically feature bundles. These are bundled options. You and I walk into a showroom and we look at a car we really like, and we are not allowed, it's just not available for most cars. I can't say this is true across the planet, but for most cars, you are not allowed to go down a list of the 1,000 options and pick yes, no, yes, blue, yes, open, fast, blue, yes, no. You're not allowed to do that. Your options come in packages, come in bundled packages. I want the sports option. All right, well, that gets you an engine and a braking system and, you know, fancy paint and pinstripes and trim in the car and maybe race modes, whatever. I want the off-road option. Well, that's a bundle of choices that the manufacturer makes for you because they can more efficiently manufacture the vehicle if they limit the choices that are available. And so that's what a feature bundle overlay is. It's just a constraint. It's a set of, what's the word I want, sort of constraining guideposts that kind of put the consumer at that level, into narrow paths that they can choose. And so it's just a set of constraints. If you pick, you cannot pick these options separately. This is the combination of options that you're allowed to pick at this level. So that's a bundle overlay. We've provided it, as I said, at the highest level, but the concept works all over. And so looking back, here's where we've come. This is the journey that we've taken in about 35 minutes. And we started down at asset variation points way back when I was worried about making sure that this line of source code did occur in this product but didn't occur in that other product. And I've come all the way up to system feature models, and I've added this concept that could overlay any one of these levels called feature bundles. And we find if we've done the arithmetic on this, again, a large automotive product line is our test example here, that now I'm in the world of about 1,000 choices, sort of 2 to the 10th. That's manageable. That's something that people can get their heads around. That's something that consumers can get their heads around, the manufacturers, the portfolio engineers, the people who are deciding where the portfolio is going to go in 10 years and so forth. They do not want to talk about lines of requirements. They do not want to talk about primitive features. They do not want to talk about even component models. You know, they want to talk up at these very, very high abstract levels. And so we started by asking, what is a distinguishing characteristic? That's where we ended up. The answer to a distinguishing characteristic is it depends on who you are, about what a distinguishing characteristic means for you. And with this feature ontology, I believe that we've now arrived at a point of maturity in product line engineering where I've got I won't say formal, but a well-structured way to think about what distinguishing characteristics and variation means at a set of levels that seems to have held up well in practice. Who's using this? So I'll just go over a couple of these. These are our customers, so I can share this with you. We've published with each of these and others as well. And I'll just point to the third column right there. That's General Motors. So we publish papers with them. I can share that with you. General Motors doesn't really like people putting their logos on slides without permission, and so we respect that. But I can tell you who it is. And they are looking at they're rolling out this approach and including the ontology. And they're finding it very helpful to help inform the various people of their thousands of engineers and engineering management and executive leadership to use this to be able to talk about the features that they use. And you can see some of the numbers down there where we're applying feature-based product line engineering to these various companies and organizations. And you can see the payback. So it's why those of us who work in this field, I would say, are passionate about the field. These numbers are amazing. They continue to be amazing, and we don't see anything else that comes close. So that's why we're doing what we're doing. And we think that the field now has reached a point of maturity where we're ready to standardize on what it means to do feature-based product line engineering, what it means to have that factory picture that I showed you before, shared asset supersets with variation points written in terms of features from a feature catalog from which I derive a bill of features. That whole model that I showed you in the beginning is going to be instantiated in an upcoming ISO standard with involvement and support from INCOSE. So our representation to ISO is under the cloak of INCOSE, the Product Line Engineering International Working Group. And so that's where we are taking this with INCOSE's help and encouragement and support. And we expect that the feature is, the standard will include a feature ontology similar to the one that I've just presented. So with that, I will say thank you for listening. I hope you've enjoyed this. I think this is a new threshold of product line engineering where we're getting a little bit more mature about what we mean by feature-based product line engineering, this paradigm that we've been prosecuting for, in our company, 16 years now. And I think we're seeing it grow up, and it's getting some nice intellectual accompaniment to it. I think that helps it be easier to explain and to apply in large organizations. And that's what we want to do because we think that large organizations who build product lines, they ought to be doing this. So I'll stop at this point and ask for questions. Thanks very much.
Paul, thank you for a great presentation on feature-based product line engineering for the enterprise. At the moment, we have no questions from the audience, so don't forget, if you want to ask a question, write it in the Q&A box, and it will appear, and I will ask Paul. So we'll give a minute or so for people to ask questions. Oh, we have a question. Oh, some questions are appearing. So the first one is from Adam Hawley. What would be the timeline for the adoption of something like this?
That's a good question. I really like that, and I'm going to give you the good consultant's answer, so it depends. Adoption of this, I would say, is a journey, so it's not an event. This picture that I showed you, where I've got all my shared assets wired up with variation points, I'd say that's an end state, but you certainly don't have to start there. So you can, there are many ways to adopt this incrementally, we find, and get improvement almost immediately. So you don't have to do the whole journey in order to get improvement, immediate improvement. We like you to take the whole journey, but that could take years. It could take several years for a large organization, 5 years, 6 years, 10 years. That's not out of the question for a very large, 100,000 engineer organization. But for small organizations or parts of a larger organization, you can do something and start to get benefit in a matter of months. And so you don't have to do this whole picture. Pick a shared asset where you might get, really good return on investment and just do that for now. Or pick a subsystem, or pick a small product group, or pick a couple of teams that are doing kind of duplicative things and merge them. So there are ways to start and get benefit in very short order. I would say a matter of months is not out of the question. For large organizations, the full story, the full journey may never be completed, and that might take years. I've got a customer in Japan. They make chips. They use gears to configure one shared asset, Word documents that are their user manuals. That's the problem that they had. They hated having to manage duplicative information across multiple manuals. They're doing one thing. I wish they would do more. I wish they would expand their notion of what's in their V to do more. They're not. They won't. They're fine. They're getting benefit. It didn't take them long to do that at all. So that's how I would answer that. Right? It's a journey, but you can start the journey and start to get benefit pretty quickly.
So the next question is from Lenny Noyce. Can you explain more about the automation part of PLE?
Sure. In feature-based PLE, and I'll just leave this slide up because it's the one I want to really appeal to, the automation lives in the configurator. So our configurator has two functions to it. One is it is the home, it is the environment in which you create the feature catalogs and the bills of features. It's the home of features. And our configurator implements the ontology that I just showed you in various tool-specific constructs that map to those different ontological levels. The second function that the configurator does is it applies the mapping between the shared assets over here with variation points that are predicated on feature choices. It maps those to the actual feature choices associated with a bill of materials. So let's just pick a software file. I want the software file to be used in product A but not product B. Well, why? Well, it's because product A has a feature that product B doesn't, and that software file helps to implement that feature. And so that software file then would be annotated with a predicate that says when that feature is chosen, select me for inclusion in the product. And so the configurator here just executes that. It says, fine, I'm building product A. Oh, that feature is turned on, so that software file, yep, that should be included, so over it comes. But now I'm building product B. Let me check. No, that feature was not included, so that software file said I shouldn't be there, and so that software file does not show up in product B. That's the function of the automation. Feel free to elaborate if that didn't help.
Thank you. Next question is from Dave Walden, who says, good talk, thank you. Much of this was presented from documenting an existing architecture. Could you comment on how this can be used to ensure the feature set of a new system is the best?
Oh, good question. I have to think about that. You're right. It did come from, we are often informed by existing systems where we come about saying, you know, what are the differences in your systems. I would hypothesize, I would posit that even if you are thinking about a new system, if it's a brand new product line, let's say it doesn't exist yet, you still must be thinking about members of that product line, members of that product family, and you've got to be thinking, I would posit, about how those differ from each other. And given that, as soon as you start talking about how two systems differ from each other, we're in business. So we can help you say, fine, what is the characterization of those differences? And we can find the right abstractions, and those turn out to be features. So you are correct that most of our experience and most of our material for this comes from people saying, I've got different existing systems and I'm tired of it. I want to, you know, make them a product line. Fair point. But I'm going to hypothesize for you that even if you don't, we can still do this. As long as you're thinking about the differences of the members of your family, whether they exist or not, we're in business for you.
Next is an observation from John Clark. Would a better name for feature bundle overlay be System of Systems feature model?
Good question. Oh, what a prescient question. I love that question. Charlie Kruger, our company's founder, presented a paper version of this at the International Symposium a couple weeks ago in Adelaide, and his last level was System of Systems feature model. And he got questions about that. People seemed to start reading architectural meaning into that wasn't there. And so we decided to retire the term System of Systems feature model. But if you want to think of it that way, I think you're right on. Now, I think the overlay construct is actually orthogonal to that. The Systems of Systems feature model is just continued aggregation of lower level constructs into more and more, what shall I say, more and more complex primitives that can then be combined at others, and you can do that ad nauseum. We sort of stopped at level 4 because we said that's as far as we need to get for the largest product line on the planet. So that was an empirical stopping point, not a theoretical stopping point. But the overlay is an orthogonal concept. At any level, you can, all it does is say, rather than picking from the offerings of my children in an unlimited way, I'm going to restrict how I pick the offerings from among my children so that at my level, I'm limited to a small number of combinations. So it's a little bit different, but I'm okay with System of Systems model, feature model. I think that's okay. We just sort of decided not to go there.
So next question from Carl Barker. Within the various organizations where this has been deployed, has this been led by the electrical engineering department or the vehicle engineering department?
Depends. So not every place where this has been deployed has an electrical engineering department. We have examples where the answer to your question is yes, and we have we have cases where the answer to your question is no. Other folks did it. So, for instance, one of the case studies that we talked about is a product line of training systems for the United States Army. It's built by General Dynamics. They're the prime contractor, and they're using this approach to configure software code, but also the bills of materials for the parts and the equipment that has to show up at a training range, and also the maintenance documentation for when the system is deployed on a training range, so that the soldiers really can go into a room and know how to fix something that's broken. So they really don't have the notion of an electrical engineering part at all. And so, again, the answer to your question is sometimes yes, because the product line engineering field, I think, at least in my trajectory through it, came out of software. And so software and electronics make a natural home. But sometimes the answer to your question is no, and I think we've actually reached neutrality with respect to that at this point of maturity of the field.
So a couple more questions from John Clark relating to feature. Would function be another name for feature? And would user story, for instance in Agile, be another name for feature?
Feature to us, remember, is a distinguishing characteristic. So if if all products in my product line do a thing, if they all have a function, I would not capture that as a feature. That would not serve to drive any difference at any level, and not even any of the shared assets. So if everything does a particular function, every product carries this out, it's just what everything does, then all of the shared asset content that manifests that common function is going to be the same across all products. And so I'm pretty confident in saying, no, I would not want to call a feature a function. I do not think those are interchangeable. And as for user story, again, same thing. I want to get the concept of distinction in there, a distinguishing characteristic. And features are not all visible to the user. So I kind of would want to stay away from that term as well.
Okay, we have no more questions from the audience, but I have a question. Did you find much of a cultural barrier to introducing this concept in some of the organizations that you've dealt with?
No, we found a cultural barrier introducing this in all of the organizations that we dealt with. We're asking people to change the way they think a little bit, and we're asking people in organizations to change the way they build their products. And that's not an easy sell. So you saw some of our numbers that we've seen in terms of improvements. I can show that chart all day long and then ask, why isn't everybody doing this? Why aren't they? Why isn't everybody doing this? And the cold hard truth is they're not. Not everybody is doing this, and that's what makes the case studies and the success stories, I think, continue to be valuable to continue to build this sort of overwhelming body of evidence that if you're not doing it, you really ought to be doing it. So it is the cultural change that is the impediment. And there are whole talks, a whole organizational change community that's sprung up that helps organizations change. And we do leverage a lot of that intellectual capital as we go into an organization, help them change. So we used to think that this was a grassroots, I mean, way back in the early days, we thought this was a grassroots kind of thing. We could get the engineers to do it and it would just spread. Not so much. So now we very intentionally reach out to executive leadership and say, you cannot sit on the sidelines for this. You cannot watch. You have to be in there, and you have to be eliminating roadblocks and obstacles, and you have to make sure that this is the most important thing in your whole organization. Otherwise, inertia will take over. Yeah, so that's a whole other facet of this.
So we have another question from Jim Teef. Have you applied this to an organization building SaaS application with thousands of microservices?
We have applied it. Hey, Jim. We have applied it to organizations doing SaaS. I will have to say probably not at that scale.
The question from Carl Barker. In the organizations where this originates from a department that is not responsible for the whole product, does this reach a point where it needs to transition to the department responsible for the whole product?
Yeah, if I were in charge of the world, I would say yes. Yeah, of course it does. You know, why wouldn't the whole world the whole department want to do this? But you know, I'm biased. But I'll go back to what I said earlier, that this is a journey, and if this can take root in a particular part or subpart or department or subsystem or shared asset group, then you're going to be better off. So it will bring savings. And many of our deployments are like that. A particular group said, this is great, this is really going to help us, and we're going to do it. And, you know, and they look around and they say, why aren't the rest of you doing this? And they do or don't for whatever reason. But those individual groups are applying it and getting good results, and they're happy. Again, if I was the emperor, you know, I would say, everybody do it, but I'm not so much the emperor. Darn it.
Okay, Paul, thank you again for a great talk, and thank you to the audience for your questions and your time. Could you go to the next slide after the end of your presentation, please, Paul? Okay, and the next one, please. Yep. The next slide shows our upcoming schedule. The next webinar will be held on Wednesday, 23rd of August 2017, when Ian Pressland will give a presentation on the NCOSE Certification Program Competency Areas Update. Then on Wednesday, the 20th of September 2017, Rick Dove will give the next presentation in his series on Agile Systems Engineering, Agile Systems and Processes 106, Risk Management and Mitigation. Additional webinars will be offered on the third Wednesday of each month through 2017. And please note that if you go to the website shown here, you'll see more information about the webinar series, including a way to view the last 101 webinars and soon this webinar as well. Next slide, please. Please note that the 11th NCOSE Great Lakes Regional Conference will be held in the Twin Cities, Minnesota, USA, on 11th to 14th of October 2017. Next slide, please. As mentioned earlier, you can now claim 1 PDU credit towards your Systems Engineering Professional Recertification by attending this webinar. You may also claim this credit retrospectively for NCOSE webinars that you have attended and where attendance meets the qualification requirements. Please contact NCOSE if you wish to know which webinars you attended and if you met the qualification requirements. Thank you again, and goodbye.